when we talk about collisions, there can be two types of collisions. One of the types of collisions is called an elastic collision. And with an elastic collision, the two objects will bounce apart after the collision in such a way that all of the kinetic energy they had at the beginning of the collision will remain at the end of the collision. So, as you can see up there, it says, for an elastic collision, the two objects bounce apart after the collision, and then it's with the star here I've put, the kinetic energy is conserved. Underneath it I put momentum is always conserved because it is. In the other type of collision, called an inelastic collision, what happens is there'll be two objects coming towards each other and they're going to collide, and after the collision they may stick together or they may bounce apart. We don't exactly know what's going to happen. So here I've written these two objects may bounce apart or they may stick together. If they stick together, most books call that a perfectly inelastic collision. So I've written that here. If the two objects stick together after the collision, it's called a perfectly inelastic collision. The last sample problem we did, I believe, was a perfectly inelastic collision. Some books call it, our book calls it a completely inelastic collision. Many books call it a perfectly inelastic collision. And in this case, the kinetic energy is not conserved. So what does that mean? The kinetic energy is the energy of motion. So the two objects had some kinetic energy. They were either both moving or one of them was moving, but something had to be moving if there was going to be a collision. So the motion energy before the collision will not all be conserved. Some of that energy that was dealt with, some of the energy from motion is going to be converted into sound. So when two things collide, most likely you're going to hear a bang when they hit. Think of anything. Think of two people colliding, you hear a bang. Think of two cars colliding, it's an incredible bang. Think of two pool balls, colliding. There's always a sound. And what happens is sound is energy, and the energy that the sound was created from came from the speed energy. So in real life, there is no such thing as an elastic collision. The closest we can come to an approximate elastic collision would be the air molecules between everything right now. There's air molecules between me and this camera, and the air molecules are moving through the air and colliding constantly with each other and with us, and that's as close as we can get to an approximation of an elastic collision. But everything else in the world, when we can see it and we can see it colliding, even though we may not physically hear it, if we took the best microphone system that we could and mic'd that collision, two cotton balls colliding with each other, you mic it as much as you can, and I'm sure you would hear those fibers rubbing against each other. So we can always pretend that there's no, loss of kinetic energy. We can always pretend that things don't make a sound after they collide. So this is the pretend type of a world, just like in the first half of Chapter 4 we were pretending there was no friction, and in the first half of, in all of Chapter 2 we've been pretending that there's been no air resistance. So this is just pretending that there would be no loss of kinetic energy. This is the real world. So everything that collides will collide in such a way that some of the kinetic energy of motion will be lost and it'll be converted into sound or heat. Momentum is always conserved, as I've put here. Okay, so we'll do some examples and try to show how they are working. Here's an example, a sample problem, and what they've done is I haven't written out the words for you. So the words would typically be written as a story in a paragraph form. The paragraph would be something like, you have block A, so we can call this block A, and I can call this second one block B, and block A again and block B. So it says something like, you might have block A, which is 4 kilograms, and it's moving to the right with the speed of 6 meters per second, and it is going to collide with block B, which is smaller, which is 2 kilograms. It's also moving to the right at 3 meters per second, so it's moving much slower to the right. And as you can see, block A is going to collide into it. So what I've drawn to the left here is a before the collision picture, And this little squiggly line here would represent the collision as it happens. We can't actually see what happens. This is immediately before the collision. Now what's going to happen immediately after the collision? Well, we were told that block A will be still moving to the right, but it's going to be reduced. Its speed's going to be down to 4 meters per second. And the question is, what happens to block B? What's the speed of block B after the collision? Okay, so what we could do is we can just use conservation of momentum. Now, I have no idea if this is an elastic collision or an inelastic collision yet. So I would never ever try to do any of these problems using conservation of kinetic energy, because I don't know if it's conserved or not. But momentum is always conserved, so I'll start by using conservation of momentum, which means underneath each piece I'll write the formula. So it's MA VA initially plus MB VB initially equals MA VA finally plus MB VB finally. That's what conservation of momentum says. The total momentum of the system before the collision is equal to the total momentum of the system after the collision. And I have mostly these numbers, so I can plug them in. So this is 4 kilograms, and this is 6 meters per second, plus, and MB is 2 kilograms, and this is 3 meters per second, and this equals, and this one is 4 kilograms, and this is 4 meters per second, plus, and the MB is 2 kilograms, and VB with final. So this is the thing we don't know right here. So the math there doesn't look too complicated. Just plug everything in. So this is 24 kilograms meters per second, plus, and this is 6 kilograms meters per second, and this is 16, and this is 2 kilograms. Now we have to gather our like terms. So 24 plus 24 with these units plus 6 with those units minus 16. This would be 24 plus 6 is 30, minus 16 would give me 14. So we have 14 kilograms meters per second equals 2 kilograms, and then this is times VB final. So if I divide both sides by 2 kilograms, the number 14 divided by 2 will give me 7, and the units, kilograms, will cancel out with kilograms. So I'm left with 7 meters per second equals VB final. Okay, so if the only question was how fast is VB moving after the collision, we now know. Okay, so if VB is moving at the speed of 7 meters per second, it's implied that it's a positive sign, so it's moving to the right. Now one might ask, what type of a collision was this? Okay, so if we want to know what type of a collision it is, we have to go and look at the kinetic energies. We just finished calculating V final, so it was 7 meters per second. And now I want to know what type of a collision is this? So the only way I know how to do this is to go and calculate what is the individual kinetic energy of each piece before the collision and after the collision. So I will do that. I'll attempt to do that. So kinetic energy is a formula 1/2 mv squared. You'll learn that in chapter 6. So the kinetic energy of this piece right here would be 1/2 mv squared. So I'll just plug it in. It's 1/2 m is 4 kilograms, and the v is 6 meters per second. We have to square it. So you can do this basically in your head, hopefully. So this would be 1/2 times 4 is 2, and then 36 times 6 squared is 36 times 2 is 72. So we have 72 joules of kinetic energy from this piece. And now this piece right here would have a kinetic energy 1/2 mv squared. And so that would be 1/2. The mass is 2 kilograms. And the speed is 3 meters per second, we have to square that. So again, you can do it in your head pretty much. 2 times a half is 1, and 1 times 3 squared is 9. So this gives me 9 joules. Okay, and the kinetic energy of this piece right here would be 1/2. The mass of it is 4 kilograms, and we're going to have a speed of 4 meters per second. We square that, so 1/2 times 4 is 2. 2 times 4 squared. 4 squared is 16. So 2 times 16 is 32. So this is 32 joules of kinetic energy. And this last piece right here, we would have 1/2. The mass of it is 2 kilograms. And the speed of it is 7 meters per second. We have to square that. So 1/2 times 2 is 1, and then times 7 squared is 49. So we have 49 joules here. Okay. So now I have all these numbers for energies, and what do I do with them? Well, the rule says that if it is an elastic collision, then all of the kinetic energies are conserved, meaning all of the kinetic energy before the collision. So these are the two energies before the collision. So if I add those two up, I get 72 plus 9. I get 81 joules before the collision. So this is kinetic energy initially before the collision. Now I want to see what happened after the collision. So if I go over here, I see I have 32 and 49, and if I add those up, 32 and 49, I also get 81. So I'm adding these two numbers here. So if I added those, I will get the kinetic energy final after the collision. So with information like this, this is telling me I have an elastic collision. All of the kinetic energy has been conserved. Question was, what type of a collision is this? And the answer would be an elastic collision. Okay. And I only know that just because of the kinetic energies being conserved. Okay. And with some time, with some experience, you learn a few tricks about this. If you notice the difference between the two velocities at the beginning. So for instance, if you notice the difference between these two numbers right here, if you take, basically, if you take the A velocity minus the B velocity at the beginning, you'll end up with 3. And over here, if you take the B velocity and you minus the A velocity at the ending, you'll also get 3. So if you can notice that the change in the initial velocities are going to equal the same number, then it's a hint that it's going to be an elastic collision. So here, the difference between these two, the A initial minus B initial is 3, and B final minus A final is 3. So that's also a hint that it's going to be an elastic collision. Let's look at another one. Here I have another word problem, and I didn't write down the word problem, but it would be a paragraph. It would have words, and I've already built the picture around it. So the words most likely would say something like you have a 10-kilogram cart moving to the right with a speed of 5 meters per second, and it's about to collide with a stationary 20-kilogram cart, which is stationary, not moving. And it might say after the collision, the two carts stick together and move as one. The question I have here is, find the percentage of the kinetic energy that will be lost during this collision. So I already know what type of a collision it is because we've learned if they stick together after the collision, it's called a completely inelastic collision. So it is going to be an inelastic collision, which means we will be losing some of the kinetic energy, and our job is to figure out how much. So we'll start by just basically writing the formula for conservation of energy. And we'll do that by basically putting the symbols underneath each one of these boxes. So I've identified the boxes. I've called the first box A and the second box B. And I've called the big stuck together box, I haven't called it anything yet. So what I'll do is underneath this one, I'll say mass of box A, the velocity of box A initially, plus mass of box B, the velocity of box B initially equals. This is the mass of the whole total system, and this is the final velocity of the whole thing. So the rule says that the total momentum before a collision, and here I have two things. They have momentums. They're moving. Well, this one's not, but this is the total momentum before the collision. So what I'm saying here is the total momentum before the collision, these two added up together, is equal to the total momentum after the collision. And you can basically plug in these numbers. So this is going to be 10 kilograms, and the velocity is a plus 5 meters per second. And this is 20 kilograms, and I'm multiplying it by 0. And this is equal to, the total mass would be the 10 plus the 20. So we have 30 kilograms, and the final velocity is unknown. So this comes out to be 50 kilograms times meters per second plus 0 equals 30 kilograms times V final. If I want to get V final by itself, I divide both sides by 30 kilograms. That goes, and I'll divide this side by 30 kilograms. And the kilogram units go out, and when I take 50 and I divide it by 30, the number on my calculator is 1.67, and the units would just be meters per second, and that's going to be V final for the whole thing when it's stuck together. So this whole thing will be moving with a speed of 1.67, because this particular number, they gave it to you, and it's implied that we have a positive sign in front. It's moving to the right, so I'll put a positive sign there. It's going to the right. Okay, so we need to know all of the speeds before we can figure out anything about the kinetic energy. So the question is, find the percentage of the kinetic energy that's going to be lost. So I have to erase what's up here and write the kinetic energy formula. So I could write 1/2 mass of block A, velocity of block A initially, squared, plus 1/2 mass of block B, velocity of block B initially, squared, equals 1/2 the total mass times the final velocity, which is squared. Now, a lot of times you don't know if it's an elastic or inelastic collision. So a lot of times you'd do this and you'd say, question mark, meaning, are they equal? Well, I've already used my knowledge. I've already used some of the information I have, and I know that if the two objects stick together, it's called a completely inelastic collision. And by definition, inelastic means kinetic energy gets lost to sound and energy. So these won't be equal to each other, but I want to compare them. Okay, so they won't be equal. I just want to compare the left side and the right side. So if I plug this in, it's 1/2. This is the number 10, and this is the speed 5, and that's squared. And this is 1/2, and the mass is 20, and the speed is 0. And then over here we have 1/2, and this is 30, and the speed of it is 1.67. And this is squared. So if we do this one, we would be able to do it in our head mostly. It's 5 squared, which is 25, and 25 times 10 is 250, and 250, and you take half of it, so you get 125 joules. And this one's 0. Okay. And then over here, this one's not so easy to do in your head. So let me do this one with a calculator. So this one comes out to be 41.67 joules. So all of these things together here are my kinetic energy initial, and this number right here is my kinetic energy final. The question is, what percentage of kinetic energy will be lost? Well, it's sometimes easy to look at how much kinetic energy remains. So the percent that remains basically is how much that is left divided by how much you started with. So the percentage that remains would be 41.67 joules over 125 joules. If I did that on my calculator, it comes out to be 33%. On my calculator it said 0.333, but that's 33%. So 33% of the kinetic energy remains, which must mean that 66% was lost. 66% lost of the kinetic energy. So what I've written here, 66% of the kinetic energy is lost. And where did it go? Again, when we lose energy, it's never destroyed. We just can't say we can destroy some energy and have it vaporize and disappear. It'll be transformed into some other type of energy. And if these two things are about to collide, most likely you'll hear the sound. Most likely they'll warm up the material a little bit. So there'll be some increase in the sound energy and in the heat energy, and we will lose some of our kinetic energy, the speed energy. Here's a word problem which deals with separation, not a collision. When there's two things basically somewhat stuck together, and then they're going to separate into two different parts. So we have a man, an 80-kilogram man is going to step to the right at 3 meters per second, and he's going to step off of his motionless boat, and he's going to step onto a dock. Okay? The mass of the empty boat is 200 kilograms, and I'm saying calculate the final velocity of this boat. So it's probably like a rowboat or something to that effect. So the person is right next to the dock. The person is probably standing up motionless. The boat is motionless under him. And the person just waits until the water is very calm and then has to take a step onto the dock. So the person is stepping to the right at 3 meters per second, and the person is stepping off of their boat and onto this platform. We want to know what happens to the boat. So again, I usually try to draw these things. So you see, if I were to draw it, you might have some water here, and maybe there's a dock here. Okay, so that's all we need. And the boat would be here. Okay, I don't exactly know how it would look here, but we have a person standing up in their boat, and they're not moving. Okay, so they may be standing on the seat or something. Okay. So everything is motionless here. Well, and then a moment, I'll draw this squiggly line. So in a moment, what's happening is the person has just stepped off of the dock, off of the boat. So the person now has stepped onto their platform, and they'll be moving this way to the right at 3 meters per second, and we want to know what happens to that boat that they have just, their foot has just left that boat. So we want to know. So the foot's no longer touching the boat, it's separated. And we want to know what happens to the final speed of the boat. So a lot of times I'll call these different objects A and B. So I'll call the boat A, and I'll call the person B. So the boat would be A, and the person could be B. And right underneath the objects, I will talk about the momentum. So right underneath this object, I'll say I have mass A, velocity A initially, plus mass B, velocity B initially, equals. Now that's the squiggly line. This is the moment when they separate. So you see, this is to the left is a before, and to the right is afterwards. And that's what this squiggly line would represent here. That is the moment of the separation. So over here, I'll write the mass of the boat, MB, the boat is A, MA, VA final, plus MB, VB final. So my job is to try to figure out this. I don't know the velocity of the boat. The boat has a subscript A on it, so I have to go and figure out what is the final velocity, V subscript A subscript F, the final velocity of that boat. So I plug it in. So the person's mass, A is the boat. So the boat of the, well anyways, it doesn't matter. 200 kilograms over here, but the speed is 0. And over here it's the same thing. It's 80 kilograms, but the speed is 0. Okay. Now I say equal because I'm doing conservation of momentum. The total momentum before a collision or separation is equal, that's where I am right now, it's equal to the total momentum after the collision or separation. So the mass of the boat is 200 kilograms, and the velocity final is unknown, A, plus the mass of the person was 80 kilograms, and their velocity was a plus 3 meters per second. Because it says right here they were walking and they were going to the right, so I've written 3. So underneath this, you can kind of try to simplify it a little bit. This is 0 plus 0 equals, this is 200 kg times V final A plus, and this thing here comes out to be 80 times 3 is 240. And its units of kilograms, meters over second. And we have to solve that. So I'm running out of room down here. Why don't I just take the whole thing up here? So on the left side we have 0. And on the right side, I won't have enough room there either. So why don't I try to take this up here a little bit anyways. So I'll have 0 kilograms meters per second equals 200 kilograms times V final plus, you can't see it, but the plus, I'm going to put 240 kilograms meters per second. I'm going to put that right in here. And you can't really see that. So what I want to do is I want to get the V final by itself, so I'll bring this to the other side. So it'll be negative 240 kilograms meters per second equals 200 kilograms times V final. And I'll divide both sides by 200 kilograms. Okay. So this is all gone, and on one side I have here minus 1.2. So minus 1.2. The only unit left is meters per second, and that equals VA final. What does the minus mean? The minus means that the boat is going towards the left. So if you've ever been in this predicament, you can probably identify with what's happened. You're standing on a motionless boat, and you decide to step off. You go to the right. Well, the boat is going to go to the left. So there was no momentum in the system beforehand. Nobody was moving. So when you start moving, you create positive momentum going to the right. The boat has to create some negative momentum going to the left to have an, when you take positive momentum going to the right and you add it with the same number of negative momentum going to the left, they add up to 0. So you had no momentum at the beginning. You have to also have no momentum at the end. These two will cancel each other out. Even though they're both moving, the total momentum of the system after he steps off is going to be 0. So that'll only happen if the boat has a speed of negative 1.2 meters per second.